I wanted to give us a chance to kind of bring things together for a couple reasons. There is a little bit more to say that we may or may not apply. It'll be useful to at least make comments on, though. And also, while we're here, this is, I think, just a useful perspective beyond characteristic classes. So I wanted to, again, I wanted to sum up and really discuss, you know, what do Thome cochains give us? And I wanted to give a few answers, 3 answers at sort of 3 different levels of complexity, including some things that are still under development at the end. So one, it's just a way to produce cohomology, and it has geometry associated to it. And the point is, it's from a map in, which is a good complement to sort of the usual approach. Again, what we have is if W embeds an M cross R in, which I can always arrange for any composite. So the map is really this map in F, and I just, for orientation purposes, pullback purposes, some analysis, I put that middle M cross Rn, say, that's the data. And again, it could be a vector bundle in the middle as well, which gives me this Thome class. But again, the data is mapping to M. Usually, the natural induced maps, a little bit redundant in that language, but if you have, if I want to understand the cohomology of X, well, if I have a map to X, then that gives me a place to map the cohomology of X, and maybe I show something is non-zero by showing it's non-zero in the cohomology of Z. So that's not a way to produce cohomology, that's a way to detect cohomology. So this side is detect, whereas here I would produce cohomology. And it's one of those things where it's kind of nice to actually have something that's going the wrong way, as a Thome cochain, Thome cocycle would give us. So this assumes here, of course, that W has no boundary in order to get a cocycle by what we did in the first lecture here. And again, a yoga in computing homology and cohomology is you often compare with spaces that you know. And so this gives a good complement of that. And often in practice, it's just a way then to get us a little new ingredient that can help complement the usual, you know, Meyer-Vietoris sequences or spectral sequences. To those naturally give upper bounds. Maps in and maps out can then help us produce and detect cohomology, and sometimes give lower bounds. I mean, sometimes the spectral sequences and Meyer-Vietoris sequences, quote unquote, collapse, in which case you have a sharp answer. But this can give us just one more way. It's often a bit harder. You're checking transversality and things like that, a little more delicate. You have to get to know the geometry, but I've actually used it in some research results, again, as just this little bit of, I don't know, it's like an additive to your fuel or something like that, a way to just a boost to the general techniques by being able to appeal to geometry to get some key vanishing, for example, if something is empty. Let's see. So the other answer for what it gives us more broadly is it provides a framework this subsumes one, but I think it's worth saying one. You can just produce cohomology, or really could really think of an entire framework for what we might call a complete or explicit presentation of homology and cohomology. And what do I mean by this? I mean, if I've got some module, a free module V, I want a spanning set. So let's assume that the homology cohomology is free. We can use field coefficients then to get at various kinds of torsion. But I want a spanning set, not necessarily a basis. Often in nature, you might have a spanning set and there's some relations, that's fine. But then we also would want a co-spanning set, in other words, a spanning set for V and for V dual or Hom V into the ground ring. So we get spanning sets for both that are somehow explicit, and we also want to understand the pairing between them. So it's one thing, if you're in a finitely generated free setting, then you just have the rank as the only invariant up to isomorphism. This is giving you something finer. And of course, in this case, what we would have is, let's just define a manifold presentation. A manifold complete or explicit presentation for the homology and cohomology of a manifold would mean that we have homology spanned by fundamental classes of just, well, you can either say maps or even better, embeddings. So, giving rise to, if this is F star of the fundamental class of N. So that's a manifold presentation of homology class. I've got some manifold mapping to it. Mod 2, these always exist. That was a famous result of Thome. That might be singular. It's not necessarily the second variety, a submanifold. Those are subtle questions. And then cohomology are these Thome classes, so spanned by the Thome class of Thome cocycle associated to, maybe I should use that word instead, because Thome class we'll talk about later has a different meaning of W mapping to M, again, maybe embedded in M cross Rn. Really, and so those are the objects that we sometimes can find to represent homology and cohomology, in which case the pairing becomes, well, pullback, or really, if everybody's embedded and transverse, intersection. So that's fun. When you have that, for me, that's an extra layer of just adding some geometry on top of knowing what these homology, cohomology groups, and we'll get to rings in a second, are. So what's a good example to keep in mind? Let's let M be R3 minus, well, M1 and M2. And I'm going to take two different ways I can embed a line and a circle I had them in different orders before, but anyways, here's this and this. So I'm going to take away an S1 union R in two different ways. I guess I should say E1 of S1 union R and E2 of S1 union R. And I'm just picturing what E1 and E2 are. And so what are the homology classes and cohomology classes? So let's give these complete manifold presentations. The homology classes are these H1s. These are the homology representatives. And the cohomology representatives, they need to be codimension 1 objects. Remember, we're removing these and we're looking at proper manifolds. So here's one. Just take a right half space. Or this bounding disk is another. So these are the cohomology representatives. And we see that, well, especially, we see that the pairing here is Kronecker, that especially if I move this red ring over to the side, you would see that it doesn't hit the half space. Whereas this red ring here does hit the half space, and vice versa. This lower red ring hits the disk, the upper red ring does not. And so those are the H1 and H2 reps. Sorry, the H lower one and H upper one reps. And then there is some H lower 2, namely this torus, its fundamental class is an H lower 2 rep. And what about the H upper 2? It's going to be codimension 2, so it's a one-dimensional object, and it's anything that connects this axis to that. And of course, those points aren't there, but I'm emphasizing that they approach infinity at those places. So that's an H upper 2 rep. In this case, we see that they would intersect sort of one point maybe there. Okay, the picture on the right is going to be similar. We again link around. Okay, and now it's even easier to see that the H1 is Kronecker. We still have an H lower 2, which say just contains that complement of that that circle that encapsulates it. And you might say, well, what about encapsulating the line? Well, you know, that's of course not going to be finite. And sort of morally, if I think of these as S3 minus, I've drawn this as R3 minus axes, but that's also S3 minus a union of 2 circles. Then we would see that this torus can be used to encapsulate either of the circles in both cases. And so I use the wrong color. Let me be consistent. So here's my H2 rep trying to encapsulate there. And then my H upper 2 rep is again gonna go between these and again hits the torus once. So those are complete presentations. What can you do with a complete presentation? Well, in some cases, complete, and especially our geometric or manifold presentations can be used to calculate induced maps. Sometimes that's really important. The simplest case is sometimes you want to show that something's zero on homology and cohomology. You could actually show that some pre-image is empty. But more generally, what would you do? You'd pull back. If you want to do an induced map on cohomology, you pull back, and then that means taking the pre-image and then you're intersecting with your homology representatives of your domain. So you need complete presentations for both. Or another application is that you can calculate cut products. So in this example above, the H upper ones and H upper twos behave differently. Let's see, sorry. Why is this not? Sorry, I'm having a hard time with the board on my iPad. Okay, that's better. Sorry about that. So how can we calculate cut products? I'm going to be brief because I did want to make this a reasonable amount of time, and I wanted to talk about an example. But here, let's redraw. So what are our H upper one representatives again? They're these green manifolds. And what we see is that in the first case, the intersection spans the two removed objects. So the intersection is a representative for H upper 2. So that cut product is non-trivial, where here the intersection is empty. And so that means that we have a zero cut product. Okay. Let me give an exercise. Namely, to consider Well, first, let me give another example. And that's, we're going to start with configurations of 2 points in R3. So what is this? This is the space of x1 and x2 in, or let me just do R2, sorry, just to, then all our drawings will be easier, in R2 cross R2, such that x1 is distinct from x2. And then it's pretty immediate exercise to see that the way to really think about just two different points in a Euclidean space is to take their difference and just think of that as take the unit vector in that direction. And that is going to give me a point, in this case, in S1. And you realize that, well, up to translation, I could make, say, x1 at the origin, and up to scaling, I could make x2 a unit. And translation and scaling are contractible, so that's a homotopy equivalence, that map. But again, let's play the Thome cochain game and realize that if I've got my x1 and x2, I'm going to have homology and cohomology classes. Actually, my homology was what, red? So that was, that's one homology class. X2 orbiting, again, with this S1, that makes sense. And then for the cohomology, I'm going to sort of set a detector out from some direction. And the cohomology generator says when we'll sort of light up when x2 minus x1 is some fixed direction. So we'll define B12 is when x2 orbits x1, and alpha 12 is when, sorry, let me, alpha 12 is when x2 is in a fixed direction. Okay, so then we can, so that's a complete presentation for the homology and cohomology of configurations of 2 points in the plane. And then the exercise is, get this, for configurations of 3 points in the plane. And it's got a few parts. First, you'll need to use Meyer-Vietoris for intersections. So this sits inside, of course, R2 cubed, which is contractible, but it's the intersection of various subspaces. So inside, I can think of first, and I'm just going to name the conditions on the xi. So I can think about just x1 distinct from x2 is a subspace, or x1 distinct from, or x2 distinct from x3, say. And then I can take their intersection or I can take their union, and run a Meyer-Vietoris there to notice that I'm getting more and more conditions. And then finally, if I call this space Y, I can take Y and I can take the final condition, which was what? X1 not equal to X3, and run Meyer-Vietoris in that case. And so this is Y, and this was one Meyer-Vietoris sequence. Another Meyer-Vietoris sequence has different spaces here and here. And then this ends up being configurations of 3 points in R2. And what we deduce is that the homology is, and the cohomology is rank 3 in degree 1, and in degree 2, it's rank 2. And then finally, so that's the first, that's the additive story. Then we have these, you check that the alpha I, J, and Bij still generate H upper 1 and H lower 1. We need some new H upper 2 generators. Well, and then H upper 2 is given by products of the alpha ij's. H lower 2, I'll just sketch for you. It looks like this. Here's an S1 cross S1. In the space. And we get that the H lower 2 is actually generated by such classes, and it's then helpful to pair the H lower 2 and H upper 2. And then finally, I wanted to say that there's 2 ways to understand the relations in the cohomology ring, or 3 ways. There's and what is that? That's just, in this case, alpha 1, 2, alpha 2, 3, plus alpha 2, 3, alpha 3, 1, plus alpha 3, 1, alpha 1, 2 is 0. First, there's a little symmetry argument that one can say that there must be some relation of this form. Oh, by the way, because it's pulled back from the cohomology of S1, any alpha ij squared is 0. Secondly, we can use the pairing between H2 and H upper 2. And finally, what we could do is the following. We can define classes COLI, where instead of alpha ij, which is in terms of 2 points, what we have is a collinearity of points I, J, K. For example, I could be 1, J, and K are 2 and 3. I is the important one. It's the one in the middle. So COLI is, you can check a codimension 2 submanifold of configurations of 3 points in R2. And then the point is that you figure out, well, it's again codimension, sorry, it's codimension 1. So the Thome class of COLI is an H1, and then you calculate what that is, And then here's this lovely fact that because COLI doesn't intersect COLJ, that means they're Thome classes. If I and J are different, there's a relation there. Okay, I'm going to stop now. I've got some, I've got to run off for a moment, but what I'm going to do is